we had an interesting development this week in Cammie's model. Of course, if you guys were watching last week, Cammie presented once again, part of her model with Karen B, where they were talking about how the moon is basically undulating up and down opposite the sun, and kind of in concert with the sun, and it causing the different phases and stuff like that. What we didn't really cover too heavily last week, but we have covered before, is the idea that we have come up with, that the Earth, that the moon could possibly be some sort of a rock in the sky or a mineral. And being as how Cammie is a certified gemologist and worked in the industry forever and has basically just been a rock hound her entire life, she's very interested in rocks, something that I honestly never had any interest in until I met Cammie, and then I find out all these really cool things about rocks, and I can see where people really get caught up in them. But so she and I actually were talking, I don't know, a long time ago on a particular hangout, where we were talking about the possibility of the moon being celestite or celestine. And we listed out a whole bunch of very interesting things about celestine, especially when you look at what the occult has to say about celestine. It is related in every way, shape, and form possible to the moon. Which we thought was pretty interesting, especially since Cammie was looking for characteristics specifically in celestine that would kind of match what we see in the moon. And of course we found all kinds of them. We found that it illuminates in different colors depending on certain static fields that that are passed through it or within it, or even other factors which we're going to touch on here in just a second. But suffice it to say that it's very interesting that celestine has all of these characteristics that we seem to actually see in the moon. The inclusions, the way that it fractures, just several of the other characteristics of it. Well, Cammie was looking at some of the thermal characteristics of celestine this week, and in light of what we were saying with her model last week. And so Cammie found something very interesting in the thermal characteristics that seemed to even further support her model about the moon actually being the cause of the eclipses. And of course, as you know, last week we were kind of left with a big question mark over our head. There are so many things that indicate that it could be actually the moon doing it, not to least of which would be that that's precisely where the moon should be, but also that the Rahu Ketu definitely has its merits as well. So I'm going to turn it over to Cammie really quick and let her kind of tell you what she discovered about celestite.
When looking at celestite, I do want to say it's a little bit backwards. I was looking, even for years, not looking at the moon and saying that what I see, especially when we blow it up with the P900, is remarkable. It's just like working under a microscope, working under the telescope and working under the microscope. It feels the same to me. It feels like a gemstone. Now, I did work with jewelry and not minerals so much, and so the minerals was a learning, and I actually even stayed away from the celestite a little bit, just thinking it had too much of a fluffy reputation or wasn't, the information I was pulling up, I wasn't getting, I don't know, I was just almost staying away from it, and I came back to it, and I'm glad I did, and I'm glad looking at it scientifically, I'm going to tell you some things, why I think the moon might be a mineral, and why I think it might be celestite. Part of my thinking is in this, world, and I will say on here, I believe in God, and I don't, know how he works, but I look and see how God creates things, and God creates things with minerals and with atoms. And I mean, in other words, the way I see it working around, that if you were going to build a light, you would build a light using not us manufacturing and putting pieces together, but somebody's much more brilliant than that. Somebody, you would use something that would grow and function naturally and not need wires and the such on it. So I started reading about different materials and looking for different qualities that might make sense, and everything started cross-referencing. So we're going to play a little bit, and I'm going to tell you a little bit about strontium, which everybody thinks they know, and I'm going to read a little bit from here from you. because I don't think people on minerals see it. I think it's hidden from us a lot. Strontium occurs commonly in nature, ranking as the 15th most abundant chemical element on Earth. Only 2 minerals contain sufficient strontium, however, to be used commercially to produce strontium compounds. The first one, strontiate, I'm probably doing it wrong, strontium carbonate, has a higher strontium content, but celestite, that picture that we were showing you before, celestite, which is very abundant on Earth, strontium sulfate is by far the most abundant strontium material. Virtually all strontium compounds are processed from celestite. Because celestite commonly occurs with barium and calcium, they co-occur with them and have similar properties. They look for the raw with the higher end to pull down. Now, if you scroll down a little bit, it's going to talk about the processes and where it was found. And let's see, what do you use strontium for? Strontium was used as a faceplate glass to block X-ray emissions from color cathode TV in older television models. It was used to block out the models. And at its peak in television glass, as much as 75% of U.S. strontium consumption was used in CRTs. Now, today, what are the leading uses? Today, the leading uses of strontium compounds are in ceramic ferrite magnets because of its beautiful magnetic qualities, pyrotechnics, and signal flares. Strontium ferrite magnets are commonly used in small motors, loudspeakers, electronics, and toys because of their favorable magnetic properties and low cost. Strontium can also be used in the production of zinc as a corrosive inhibitor in paint and to improve castability in aluminum alloys. So we'll leave it there a little bit and say that this is how celestite grows. It's amazing. And it's man that manufactures different things out of it, man that makes things that glow out of it. But naturally, on its own, one of the factors that fluorescent naturally has, not all celestite, but a phenomenon that occurs in some celestite and in about 15% of minerals in general, but celestite is one of them doing it, is fluorescence. Now, fluorescence, again, you'll recognize it. It's just the ability that if you have non-visible light in your UV spectrum to excite and cause a chemical reaction, a natural occurring reaction in different minerals and stones. And again, they did this on the you'll also notice this effect like in jellyfish and different, it's natural lighting is what it is. And do you have any questions so far, or is this making sense so far?
It's making sense so far. I will throw in there that strontium, of course, I've been very familiar with its use in CRTs. And it's one of those things that if it was not put in the CRTs, basically anybody watching a television or anything with any type of cathode ray tube would be irradiated literally to death because it would just bombard you with X-rays. And that's one of the things that's really quite amazing about it, is its ability to absorb those X-rays and deflect them and anyway keep them away from you. So that's very interesting that they're using that. And of course, I don't need to tell many people that have researched chemtrails that strontium is like the number 2 ingredient behind aluminum, and then of course there's barium also, but they are doing something in the atmosphere with strontium. And of course, given strontium's connections to the moon and to and with its magnetic properties, it kind of makes you wonder what's going on when you're thinking about CERN and stuff like that. So that's just the comment I wanted to throw in there, and I'll give it back to you, Cami. Go ahead.
Okay, what I'm doing is I'm reading, and we'll drop it to, you can just put what you have up there, but I'm reading from a Harvard study, basically, and what it's saying is it's talking about in fluorescence, which fluorescence occurs naturally in about 15% of the minerals out there in the world, and when it exists in a stone, it does not exist in all of them, but again, you can roll it out to this. I'm reading a study that talks about, in addition to the composition and the exciting wavelengths that several other factors may have a bearing of the presence or absence of fluorescence in minerals. What they did is they did a group of 66 minerals, of which about a third of were fluorescent at room temperature, and they cooled them with dry ice. They did temperature readings on minerals and the effect that temperature had on minerals in fluorescence. And what they came to, and again, we will drop this link, I am doing a Harvard study here, is that the change of temperature proved to be the most effective of the techniques employed. In general, increasing the temperature of mineral quenches temporarily any fluorescence which may be present, and reducing the temperature either temporarily increases the intensity of the fluorescence present, or, and what we're saying in this, I'm jumping over it, is what you're saying is it has kind of a Curie effect. If you have a mineral that is fluorescent, when you're looking at this screen here, when you get up to about 170 degrees, I'm going to do celestite. Each mineral has its own little point.
170
the fluorescence will
Celsius.
170 degrees Celsius.
Right.
The fluorescence will start to fade. At 200 degrees Celsius, the fluorescent effect will just shut down. It will no longer fluoresce. The temperature rises and gets cools to 170 degrees again, it's going to start to appear and get stronger. Now, it's going to do that through the temperature gradient. The colder it gets, the brighter the fluorescence is going to be. So the more you hyperchill, the more fluorescence will exhibit.
Okay, so let me summarize it then. So basically, what she's saying, guys, is that as the moon is undulating and going around, and you get the new moon and the sun are sitting right next to each other, which would kind of tend to indicate that the sun would have the greatest heating effect on the new moon. Now, what did we just find out? We just found out that in celestite, when you go over, what was it, 150 Celsius, 100 and whatever it was, 170
yes.
degrees Celsius, it starts taking away its luminescent characteristics. So that would go along absolutely perfect with what we're seeing. So when the moon is full, and of course is the furthest away from it, which would be the coolest point theoretically when it's over here on the full moon, it would be at minimum temperature, which would indicate, for celestite, maximum fluorescence, right? And of course we get that full moon. So this is a possibility that we're throwing out there to people, that what's actually happening during the new moon is it's being superheated by the sun, and the mineral content within the moon is actually then retarding the fluorescence fluorescent capabilities or characteristics of the celestite. Which to me is absolutely amazing that it goes perfectly along with that line of thought.
Now, again, these are only possibilities, but as you read the possibilities and you read, the different information, and this is very similar to the last article that I brought up or was reading from, but this is another co-effect that would be taking place to celestite. Not only does it have a fluorescence effect with the temperature or thermal effect on that, celestite and many stones themselves also have a color morphine that naturally occurs in stones. This has nothing to do with the fluorescence, but you'll read this one. It happens to coexist at the same time as the fluorescence. So this one, the common blue color of celestine bleaches out at about 200 degrees Celsius and reappears upon X-ray irradiation. The thermoluminescent maximum for blue celestite also occurs at 200 degrees. So what this is saying is at 200 degrees Celsius, not only do the lights go out as far as fluorescing and glowing, but the whole stone pales. It fades. So when people say, how can the moon disappear? A possibility on how the moon could just disappear if it was a rock is this particular rock totally fades out at 200 degrees Celsius and all lighting capabilities shut down. To me, that would be a way that it could disappear.
Right. Now, there was a question from the chat that says, what about the cases when we see the full moon during the daylight? Well, I think that, in my opinion,
no problem there.
Yeah, that's not a problem because, full moon, again, the full moon would be at its furthest distance. Whether or not it's in the daylight or not, you would have the maximum charging capacity from the sun, if you want to look at it that way. But also, being the furthest distance from the sun, it would also be technically the coolest point away from the sun as well. So that would actually work out perfectly.
I agree in that too, and putting the, again, there's so many different pieces to put together. And I am not saying the moon is celestite, but I am saying it certainly is a strong possibility. And the more you look at it, the harder it is to rule out, when I'm looking at the related optical effects and things that we get on it. I think when we're looking at, how our world is built and how it grows and the different pieces of it, it's called electrical properties of rocks and minerals. When you go into the electrical theories and the electromagnetic world, I think everybody needs to know that when you're looking at rocks, each rock has a polarity. They all have very specific conductor, dielectric, polarizing. They have all of the conditions necessary. In other words, a rock can be a conductor. A rock can be. They are the electrical properties of material defines its behavior. When an electric field is applied, the two principal electrical properties are the dielectric constant, which is the measure of the electric polarization that takes place when the electric field is applied. All rocks are measured by these properties. And this is just giving an abstract on it, but you can see page after page after page of this if you do any research and get your information. And again, all of these things are also extremely affected by temperature, which is very interesting. Temperature seems to be always a compounding factor.
Yes, it definitely does. As temperature is a compounding factor in a lot of things, especially in electrical circuits. Temperature definitely has its very distinct influence on any model that takes that into consideration. So it's very interesting indeed. Who would have thought rocks would have characteristics like that? Of course, before I met Cami, I never really thought about magnetite and how magnets are made and naturally magnetic material and stuff like this. But I can see where people really get interested in rocks now, because the more I look at it, the more interesting it is. And also, one of the guys that we've been highlighting, and we'll be talking a little bit about his work today, Chris Monk, apparently worked as a geologist and had some very interesting information to share about that, especially the drilling down of 12 kilometers, or basically 8 or 9 miles, something like that, as far as what they hit and its composition that he described when he was reading the geologic reports on it, which was very, very interesting. But okay, so we'll drop that for now.
At the top of the page to the left, you'll just notice, and it's showing how diamonds can fluoresce, but what it's also doing is it's giving you a nice gradient. When we say going from out to hyper fluorescent, you can see like the different levels shown just in the gradient there when it's again showing how different diamonds do it. But I thought that was a nice visual, even though it didn't apply. But if you scroll down to where you were, I thought that was a great visual. These are all diamonds, by the way, and again, diamonds are a mineral or are a rock. And this just shows a whole bunch of diamonds with no visible lighting under a black light, under UV light. And again, how people don't really realize all that's right in front of them, that they don't see it. All this requires is ultraviolet light to see this in a dark room. And it's there. Other than that, if you look at the picture, they're all different. The one thing that I should probably say about fluorescence is a blue stone does not necessarily fluoresce. The color that it fluoresces can totally change. These stones are different colors underneath it than the colors they're fluorescing. A blue diamond can fluoresce red. Even within the different color things, the color that they naturally have does not represent the color they fluoresce. So I'll leave it with that.
But yeah, I mean, Celestite's amazing. It really is, especially when you look at it, and when you just look at the physical similarities to the moon, it's absolutely uncanny. So, all right. So one of the things that Cami wanted me to point out to everybody, and this is really a fascinating clip. I'll go ahead and just post it in the chat here real quick, but it will be in the show notes afterwards. But this particular movie is a 1958 documentary put out by Bell Laboratories that actually shows how to grow crystals, what they look like when they grow. It's absolutely fascinating. Everybody that Cami has shown this to has been, completely blown away by it, because even I had no idea that crystals manifested and they grew so quickly. I mean, almost instantaneously. Theoria Apophysis was showing also how to grow these crystals in a matter of seconds. So when things crystallize and stuff like that, it isn't always a process that takes millions and millions of years, as we're told by the mainstream.
It never is.
It never is. Just another lie of the mainstream. So this is a movie that is really informative on crystals, and of course crystals have been studied by, admired by the ancients. They've been a part of the occult for a long, long time, and that is because of their exquisite properties and their, in some cases, supernatural properties. And of course, I don't need to say that crystals are used in every facet of today's electronics industry. Primarily as oscillators. You take a crystal lattice and you put it, you apply a voltage to it, and it'll oscillate at a very stable frequency. Quartz crystal will do that. And of course, you have semiconductors, which it's all about the crystal world. There's everything. Everything in modern electronics has to do a lot with crystals. So they're very prevalent, and they're very, very widely used. And as there are a lot of minerals and stuff, so it's very interesting stuff to study. So just want to put that out there for this Jeff Whitney video. The Bell Laboratories Crystals documentary is absolutely fabulous. And as long as we're speaking about rocks, this is very interesting. This is not that old. This article says researcher discovers a 55,000-year-old artifact made out of oxygen, which is very interesting. So it says in 1990, an Italian geologist named Angelino Pittoni was visiting Sierra Leone in the vicinity of the border with Guinea Conakry, to verify if a certain region of the country known as Kano was indeed a rich deposit of diamonds that could be exploited by that company that had hired him and sought to obtain the concession of exploitation in exchange for building a number of houses for the government. While standing in the region, Pittoni came across an incredible discovery that was for some reason left out in the cold. In an area between Sierra Leone and Conakry, after removing a few inches of soil, a full chief showed Pittoni one of the most mysterious stones Pittoni had come across in his career, a blue stone with mysterious white lines on its surface. The tribal chief told Pittoni an ancient legend which, according to them, explains why the area was so rich in diamonds. But the bottom line is they're just kind of calling this the sky stone, but they found something very interesting about it, in that it is incredibly hard. They've subjected it to temperatures up to, I don't know, close to 3,000 degrees Celsius, I believe. And it didn't seem to phase it. And then another thing that is really interesting about this, and this is very uncharacteristic of most minerals, is that this number of 77.17% of the stone was made of oxygen. The remaining percentage is divided between carbon, silicon, calcium, and other elements whose presence was almost anecdotal. But wait a minute, how can oxygen make up a stone? Well, that's a good question, and that kind of even baffled Cami a little bit. But apparently, what a lot of people are saying, Richie from Boston was doing a piece on this and was saying that he believes that this is probably part of the firmament. Now, I know we've heard about other elements or other stones that have been thought to be also part of the firmament. I think Libyan desert glass is one of the big ones that's being promoted, I think, by LSC. But this is very interesting that, it's blue, it's sky blue, and it is incredibly resilient, and it's made up of 77.17% oxygen. That's extraordinary. You have any comments on that, Cami?
I do on that. I looked at this a little bit this morning, and I am not familiar with the stone. I've never touched the stone. I would love to. I do have Libyan desert glass and have my hands on that. It doesn't look like it's going to be easy to get a piece of sky stone in Cammie's hands, which is a very sad thing. On resemblance, you say it's somewhat resembles lapis lazuli. It has the colors, but again, when people look at colors, that's what things look like, and when you test it, it tests out differently. This one, the article was interesting to me because it hit some extraordinary and made extraordinary an extraordinary in it, but there was enough. It was the 77% oxygen that I felt was the most extraordinary number on the article. Most minerals that I'm looking at, the oxygen content is closer to 15 or 16%, maybe up to 20%. You have slag. I found slag contents that were that high in the oil industry, but I was not finding, other than the slag residual, that's a very unusual oxygen content on it. And the stone to have the characteristics, again, it's going to be a fun stone to look at in all kinds of context to learn from.
Yes, very interesting. So anyway, that is just another one of those very interesting mineral things that we came across that adds potential realism, I believe, to some of the assertions, like the firmament and it being like glass across the sky. It's amazing, but there seem to be more and more and more pieces of evidence that are stacking up to kind of support this claim that's in the Bible. And it doesn't surprise me in the least. But honestly, I'm glad to see this kind of information popping forward, and it's just stumping a lot of the geologists and people in the field that have never seen anything like this because of its rarity, or they're simply not taught about it, which is a very likely possibility as well. Because if it doesn't fit into the mainstream paradigm, it's usually left behind, and it's kind of ignored at that point. So yeah, just something very interesting. Now this channel, Mystery History, did a video documentary on it. It's basically saying a lot of the same thing that the article was saying. I will put this in the show notes. It's very interesting that you're saying this. Now, some of the people in this are saying that this blue stone is lapis lazuli, and tell us why that is not so, Cami.
Because if it was lapis lazuli, you would take, in other words, when you look at a stone and you test it, here I bring up a picture of lapis on the screen, fine lapis for you. You're always going to have a lot of things that look alike when you're looking at, so yes, it does look like lapis lazuli. I could also pick up some blue soda, like I could pick up a bunch of minerals if I just sent it to you in the chat, I thought. Yeah.
I just brought
Perfect.
it up.
Oops, that's a special one in the middle. I'm sorry, I'm looking at one of the sculptures, but you'll see it when you laugh.
Oh, okay.
Anyway, if you look at the stones, you'll see it does look like it could be lapis. There are a lot of blue stones that it looks like it could be, and just by common, what people are used to, lapis would be the most common. But when you're testing the stone, you are testing its refractive index, you're testing its specific gravity, you're testing its weight. A lot of the times, let me bring up another, like stones converge, they merge, they grow together, they co-grow. And so an unidentified is also some of the things that they said, like for instance, that when you crushed it, it was white and it lost its color. That's something that happens with a lot of rocks. It's nothing, a lot of the things they said were so extraordinary were not on the article, but it did have some characteristics that were the high heating point and the amount of oxygen in it. But just doing a visual test and saying that it looks like a stone is
yeah, and it's also not transparent either.
That's, again, it's not the material. It does not have the readings of the stone. So when they're testing it, it's not going to they actually will physically have the stone. They can put it on equipment, so they will be able to know it's not lapis. So your difference is they, like, for instance, I'm going to bring up this page here. Copy. And just because they haven't identified or when they find rocks a lot, if it just a lot of the times means it hasn't been formally named yet, and its emergence of different materials. But this, for instance, is Eyelet stone. It's found by Eyelet I pronounced it wrong, in Israel. And it's a combination of, in the middle, lapis lazuli, malachite, a whole grouping of the different stones, and it grows and it merges together in beauty. And for a while, they didn't have a name for this either. It wasn't lapis, it wasn't that, but you have a lot of merges of the stones and things that it can, it wasn't unknown elements in it. They just had not named the stone. And it's not abundant. It's not something that everybody is out there mining.
All right. Beautiful. Okay. So there we have it. There is the I Wanna Rock part of the show. And thank you, Cami, for presenting that.
This is one of those things that I think we're in danger of missing a beat, because a lot of people won't have looked at this. A lot of people won't have looked at gemstones. And once you get into it, there is so much stuff there to see. That video that you're going to drop the link in the chat notes. It's only 20 minutes long, and I would say to anybody, go and watch it. It's fascinating. There's a lot there for us to learn, and this is the sort of stuff that we've been begging for a long time. For new stuff to come out, for people to start stretching their minds a little bit. And the other one is just pick up on Cami's point about temperature, because it's almost counterintuitive. We often think about things get excited and things glow and all that sort of stuff when they get hot. This is completely the opposite side of it. It's like almost like the flip side of the coin, how things fluoresce when they get cold. And I think it opens up another option for us to look at. So again, I say to people, go and have a look at it. Go and look at the model again, and consider whether the cold is doing things. And I know that was fantastic, Cami.
This is the movie that Adam is talking about, the Physics Crystals 1958 Alan Holden Bell Laboratories, the Physical Science Study Committee, and I'll just go ahead and paste this in the chat right now, and it will be in the show notes afterwards. But you got to love these old movies that are instructional. Some of them are so incredibly good, and it's funny that at the beginning so many of them had to be declassified. It's like, really, why would they classify stuff like this unless all along they're just trying to keep this knowledge to themselves and not really let it get out in the world until it's ancient, and then it can be buried, and people never really go looking for it, or it's not so much in their face anymore where they can just find it readily. But I love stuff like this, and you're right, Adam, this is a great video. We've watched it several times. It's absolutely fascinating. This is all, of course, in support of the idea that the moon is, potentially a physical object. And Cami's theory on it is that it is a mineral of celestine or celestite, possibly some other composites. I have seen other theories out there saying that the moon could possibly be limestone, and that has
Limestone is the same family.
Yeah, it's the same family.
Limestone is talking in the same with the celestite in that it's just it's the same family.
Yeah, so it's entirely possible, and in fact, and that's one of the reasons why I'm going back and forth, because I look at Cami's model, and I got to tell you guys, a lot of times when we discuss things, more often than not, she turns out to be right about it. And normally, I think most guys wouldn't admit that, but I'm pretty proud of my wife. She's pretty intelligent, and she's got a good handle on things.
I suppose most of you have seen a crystal at one time or another, probably in a natural history museum or in a chemical bottle. Here's an unusually big crystal, dug out of a clay pit in Brazil. Here's a smaller one, broken from the side of a cleft in the rock in Arkansas. But crystals aren't always big, beautiful things like this. As a matter of fact, crystals are everywhere. The salt you use to flavor your food, for example. It consists of little crystals of sodium chloride. You can see their shapes by looking at them through a magnifying glass. Little cubical crystals of sodium chloride. Snow. Here are some enlarged pictures of single snowflakes. Each is a single crystal of water. Here's a crystal I like especially well, probably because I made it myself. It's a crystal of alum. As a matter of fact, you can make a crystal just like it. I put some directions in the film notes in case you want to do it yourself. You buy the alum you need at a drugstore and grow the crystal in a mason jar. If you do this, I'm sure you'll be very much impressed by one thing. The crystal keeps growing, maybe for a week. It keeps getting bigger, but all the time, it has plain faces, meeting in sharp edges. You can see I haven't ground the faces on this crystal or polished them at all. This is just the way the beast grows. It almost seems as if you were getting something out of nothing, something with a shape all its own, which it decides all by itself throughout its career. In order to grow a single perfect crystal as big as this, you have to take pains and let everything happen slowly. But you can see what's actually happening by letting things happen a little bit faster and looking at the business under the microscope. I'm going to take a solution of alum, which is just itching to deposit crystals, and make a little pool of it on the microscope slide, and then add a few little crystals of alum to give the alum something to deposit on. And then get myself in focus and let her rip. There they are. You can actually see them grow if I turn now to a higher magnification. The little crystals keep pretty much the same shape as they grow, just getting bigger. Naturally, they all sit down on the microscope slide on one of their biggest faces. So you see the shape of the crystal depends mostly on what the crystal is made of, and not on its size, so long as it's free to grow in all directions. Now, crystals don't only grow out of solutions. They grow out of gases. Snowflakes, water crystals grow that way. And one of the most important places where crystals grow is out of melted materials when you cool them. Here I've got another powder you can get at the drugstore called Celestite, which melts at a convenient temperature. I'll put a little of it on a microscope slide. Then I'll carry it over here to the hot plate and melt it. And now let's go over here to the microscopes. There's one growing, turning very slowly in the liquid as it grows because it hasn't quite sat down on the slide yet. It seems almost to push those flat faces ahead through the part that's still melted. Of course, you know that the whole crystal isn't moving and shoving its front along. The liquid next to the face is becoming solid and adding itself to the face. But it's doing this in such a way that the stuff added on also forms a flat face, so the crystal keeps its shape while it grows. Now, I'll melt this back carefully on the hot plate so as to leave just a little rounded blob of crystal. That rounded blob will be a single crystal, but it won't have flat faces. And I want you to see what happens when this cools down again under the microscope. There it goes, growing the faces it wants to have, filling in the hollows and squaring off the rounded corners so that its boundaries are all flat again. Notice now what happens when two crystals bump into each other, so to speak. They don't push each other around, they just stop growing where they meet because they've used up all the stuff to grow with there. So the boundary between two crystals isn't necessarily one of the natural faces on either of them. The boundary line just depends on how the crystals happen to come together. When the whole thing is finally frozen, you have a dense mass of crystals. Maybe no single one of them shows any of its natural faces, but the whole mass is made up of crystals just the same. Almost all rocks are made up this way. Granite's a good example. Here's a hunk of it. Let's take a close look at it. You can see grains of the different colored minerals which make up granite. Here's a grayish grain of quartz. Here's a grain of pink feldspar. And the little black flecks are grains of a kind of mica. And each of these grains will be a single crystal. Notice that the three things don't mix together in the solid. They crystallize out in separate grains. Before I get through, you'll begin to see why. When you came in, I was melting some bismuth in a crucible over here, and it's been cooling. And crystals ought to have formed on the sides of the crucible, so that when I pour off the part of the bismuth that's still melted, you can see them. Sometimes you can show up the crystals in a finished piece of metal by polishing the surface and then etching it carefully with something that will eat away the metal. Here's a cast brass door handle, which the manufacturer polished, and then over the years, the sweat on people's hands etched it, and now you can see the boundaries between some of the crystals which make up that door handle. In most pieces of metal, the crystals are much smaller than these crystals because they've been broken up when the metal was drawn or rolled or hammered into shape. But the metal is crystalline just the same. Well, so almost all solid things are made of crystals. In fact, if you ask a physicist these days to define a solid, he'll probably say a solid is a bit of matter that is crystalline. Of course, that doesn't seem to get him very far, because somebody is sure to ask, what do you mean by crystalline? But he's got an answer to that one. The answer comes in two parts. The first part says all matter is made of atoms. The second part says in crystalline matter, the atoms are arranged in regular order. I want to talk a little more about what he means by this and show you a little of the evidence for it. The idea is that the crystal is a pattern of atoms, a regularly repeated pattern of atoms, like the regularly repeated pattern of a wallpaper. If the atoms were flat and made a two-dimensional crystal, they might be taking up an orderly arrangement, like this arrangement of pennies on the table. In 3 dimensions, they might be making an arrangement like these bearing balls, closely packed together. Of course, these close-packed arrangements aren't the only arrangements the atoms might take. They're just simple examples of what I mean. Now, already, perhaps, you can see what these two ideas, the idea that a crystal is made of little units, atoms or molecules, all alike, and that those little units are arranged in the crystal in a regular array, you can see how those two ideas would explain what you've been looking at under the microscope. For instance, those alum crystals kept a symmetrical shape as they grew. Now suppose you had a two-dimensional crystal, like with a pattern of atoms like the arrangement of pennies. There are more atoms in solution all around it, but since the arrangement is symmetrical in the crystal, you expect pennies to add themselves on at the same rate here, and here, and here, and so on, because conditions are the same at all those places. The crystal will grow symmetrically and keep its shape, so long as nothing gets in the way and prevents more atoms from reaching the surfaces. Let me show you another kind of evidence for these two ideas. It's a kind of evidence which doesn't come from the process of growth. It comes from the properties of the finished crystal. This is the evidence of cleavage. If you've ever handled mica, you're acquainted with cleavage. The mica crystals you find in nature come apart easily in one direction and not in any other, so that you can split them into extremely thin, tough sheets. The mica acts as if it was made like a book, with a lot of leaves of tough paper. But if you actually try it, you'll get the feeling that there's no limit to the thinness of those leaves of paper. You'll feel that if you were skillful enough, you could split each leaf of the mica in 2, and then each of those in 2 again, and so on. It makes you guess that the atoms in the mica are arranged in great sheets, that the atoms are bonded together very tightly in the sheets, and the bonding forces between the sheets are very small. Just the arrangement of atoms in sheets like that is a kind of orderliness. There aren't many crystals that cleave as well as mica. Alum, for example, doesn't cleave at all, but a great many crystals do cleave amazingly well. Let me show you the cleavage in this crystal. It's a crystal of nickel sulfate hexahydrate. It cleaves parallel to this face. I'll put the thing down on a little plasticine to hold it in place. I'll take a single-edged razor blade and direct the blade parallel to the face and give the back of the blade a smart tap. She comes apart. And now look at that, as flat as you please. You may say, oh, you picked a special place in the crystal. But look, I can cleave it again, parallel to that same face, and get a thin plate out of the thing. So it isn't a special place in the crystal, it's a special direction in the crystal. Now maybe you will say, oh, that isn't any special direction. You've got a sharp razor blade and you're cutting the thing apart with it. All right, if that's what you think, let me try the same stunt in a different direction. I turn my razor blade in a different direction and I whack it, and nothing much happens until I whack it a lot harder. And finally, of course, the thing busts. And there's no nice flat face. It's just broken apart like anything else. Now let me show you the cleavage in another crystal, a crystal of sodium nitrate. Here's a crystal that cleaves in 3 directions, not just one. I can cleave it here, like this, and I can cleave it here, like this, and here, like this. By the way, you can grow both these crystals, nickel sulfate and sodium nitrate, by recipes given in the film notes in case you want to play around with the stuff yourself. Sodium nitrate has a lot of interesting properties. It has most of the properties of the mineral calcite. When big crystals of calcite were first discovered about 300 years ago in a quarry in Iceland, the scientists of that day got hold of some, and their studies of the stuff made the first big start in our understanding of crystals. As I say, sodium nitrate and calcite have many properties in common. In particular, they both cleave the same way. When those earlier scientists saw the way calcite cleaves, they had the idea that maybe calcite was made of tiny building blocks, all alike and all having the shape of little cleavage blocks of calcite. You may be inclined to laugh at this and say that calcite, like all matter, must be made of atoms, and atoms don't look like building blocks. Okay, you're telling me. What do the atoms look like? Little hard round iron pellets? Don't let me fool you with those pennies and bearing balls I've been showing you. They just show where the atoms are, not what the atoms look like. For all I know, the atoms look like 4-leaf clovers. I want to emphasize that those early scientists produced both of the main ideas which go into the picture of a crystal that we have today. First, they were saying crystals have an ultimate fine structure, the building blocks. We would call them small groups of atoms instead of blocks, but the difference is really more a matter of words than of anything else. Second, they were saying that structure has a regular array. The blocks are stacked up in a regular order, and they keep stacking up in regular arrangement as the crystal grows. It turns out that you can think of any crystal, not only crystals which show cleavage, but any crystal, as made of little blocks stacked up in regular array without overlapping on top of one another and side by side, if you choose the right shape of block. In the case of alum, the right shape of block is a cube. And you can think of the alum crystal as made of little cubes, all stacked up on top of one another without overlapping this way. Notice that I've made the main faces on the model of the alum crystal by stepping back the cubes as I piled them up. At first you might think that would mean that the face would be pretty rough. But you got to remember that these little cubes are really only a few atoms wide. Their sides are only about 1/10,000,000th of a centimeter long, and you wouldn't feel that roughness or even see it under the microscope. One of the things that gave early support to the building block idea was the fact that all crystals of the same stuff have the same angles between corresponding faces. The crystals might be very different in size. They might have grown at different rates on different faces so that they have different overall shapes, like these two alum crystals. Nevertheless, the angles between corresponding faces of all crystals are the same, so long as the crystals are made of the same material. It all suggests very strongly that each material forms its own building block, which gets repeated again and again as the crystal grows. Most crystals can't be made out of cubic building blocks, as alum can. Their building blocks don't have the same length in the different directions. For example, here is the arrangement of atoms in the cubic building block for iron. It's fairly simple. Now look at this model of the building block for garnet. It represents an elaborate grouping of 160 atoms. But this study isn't easy. Don't get the idea you can turn on the X-rays and out drops the answer. It's a very specialized kind of study. But once we know what arrangements atoms take in crystals, we can begin to ask why they take those arrangements. We're really only just beginning to get that kind of knowledge. Now, turn back for a moment to the microscope and remind yourself of what is happening while a crystal grows. Atoms are constantly arriving at the surfaces and adding themselves onto those surfaces in an orderly way. And they're doing this at an amazing rate of speed. The crystals you're looking at are growing fairly fast. Suppose a crystal grew at the rate of only a couple of millimeters a day, which is fairly slow. You can calculate that about 1,000 layers of molecules would have to be laid down per second on the surface of that crystal. And all the molecules have to be laid down in the right sort of order. I want to borrow a trick from Sir Lawrence Bragg to give you just a rough idea of some of the things that we think must go on as a crystal grows. Sir Lawrence blows soap bubbles. He blows them in a pan of soapy water, tiny bubbles which rise to the surface and collect in rafts. The bubbles behave a little like atoms because when they're floating on the water, they attract one another a little. And when they touch, they stick to one another quite strongly, as atoms do. But, again, like the atoms, they have a squashy sort of size so that they take up space. Watch how the bubbles collect together into an orderly arrangement. It's the same as the arrangement of pennies I showed you, the so-called close-packed arrangement. Notice that the rafts are made of large parts. All of the parts have the same sort of order, but the orderliness of the parts is turned in different directions so that there are grain boundaries between the parts. This is like a solid made of lots of crystals which started growing in different places and finally joined. It's like the salal after it is all solidified, or that brass door handle. When you think of how fast the atoms have to get into order, much faster than this, the more astounding their achievement seems to be. But this will give you some little idea of what a hustle and bustle must really have to go on an atomic scale. Sometimes when the molecules are very big and have an irregular shape, they're too sluggish to get themselves arranged into order. Then they congeal into a glass. A glass is very much like a liquid, but it's like a liquid in which the molecules are no longer able to move past each other. It has patches of order in the midst of disorder. The disorder is frozen in place, so to speak, and can't get itself rearranged into order. Liquids and glasses are pretty disorderly arrangements of molecules, and gases are the most disorderly arrangements of all. The only order in gases is the arrangement of atoms grouped in each molecule of the gas. Later in this course, you'll learn more about gases. But already, you can see why gases are so very much alike in a great many ways, whereas there are so many different kinds of solids. The only way gases can differ is in the kinds of molecules they are made of. But solids can differ also in the kind of orderliness which those molecules take up in the crystals which comprise the solid. I can show you this selectiveness actually happening in some of the materials you've already looked at. I'll melt some salal on the hot plate over here. There. And bring it over to the microscope and let it cool down so that it wants to crystallize. Then I'll seed the salal with a tiny crystal of alum. Nothing happens. No salal will crystallize on it. Now, I'll seed the melt with a few little crystals of salal. And you can see the salal crystals grow, leaving the alum crystal unaffected. The orderliness of alum is not the right kind of orderliness for salal, and the salal simply waits until the right kind of orderliness is presented to it. And I think now you can see what I promised you would see about granite. Why it is that the three different ingredients, quartz, feldspar, and mica, form three separate kinds of crystals in the granite and don't form just a single crystal in which the molecules of quartz, feldspar, and mica all take part together. It's because those three kinds of molecules normally form crystals with three different kinds of order. When the three kinds of molecules are all together, they can't find a kind of order which is common to all three of them. So they crystallize out separately, each in its preferred way. You know, after 20 years of growing crystals, I still find the whole business nearly miraculous. You go to the microscope to watch it, and it happens again. And you know that the atoms are at work, busily, almost unerringly, constructing something. Something regular, something orderly, constructing something which, from an atom's point of view, is simply enormous.